Greetings and welcome to another installment of quantile. This is 20 in our basic application series. Like most content creators, we try to make each installment as freestanding or self-contained as possible. But for this mini-series, we're going to build the top concepts we've already seen earlier in our foundational series and earlier back even in this basic application series. And you can see we got this crane building something like, I don't know, a great edifice of wisdom, if you will, as a metaphor. We were originally going to contract out with Disney to create this animation, but we thought that using a second-rate operation like Disney for content might jeopardize the quantile brand, so we just went with this, and pretty happy with the way it came out. This time around, we're going to kick off our practical series on hypothesis testing of a single proportion. And I'm going to start by saying that there's an entire universe of rules, procedures, methodologies, and so on that govern the specification and interpretation and use of hypothesis tests. And for the sake of sanity, we're going to consider some here at the outset as opposed to completely ignoring them and regretting it later. So first off, for any given investigation, we are allowed only a single research question. That is a single null and alternative hypothesis pair. Our hypotheses are fashioned before we look at the data, or even better yet, before the data is gathered. The mechanism that has produced or will produce our sample can be thought of as a proxy for theoretical random sampling. Now, we may hear these themes recited in different ways depending on with whom we are talking and their degree of zeal for a particular area of application. The first two rules can be bypassed so long as special adjustments or adaptations to our test procedure are made. And the third rule, of course, is inextricably tied to our definition and conceptualization of our reference or target population. In the context of performing a decision-based research hypothesis test, if we play fast and loose with these practices, we may find ourselves guilty of so-called data dredging. When highway or railway teams need to tunnel through a mountain or beneath a body of water like a channel, they often start at opposite sides and meet somewhere near the middle. So too, sort of, with a traditional decision theory style hypothesis test. On one side, we define our critical region here based on our alternative hypothesis, our pre-specified level of significance, and our assumption concerning the sampling distribution of whatever test statistic we're going to be using. On the other side, we take the result of our experiment and calculate our test statistic. And we sort of meet in the middle. Does our calculated test statistic land in the critical region? If so, we reject our null hypothesis in favor of our alternative hypothesis. Otherwise, if our calculated test stat lands outside our critical region, we do nothing. So what we're going to do here is we're going to set up a simple example of using the normal approximation to perform a statistical hypothesis test of a single population proportion. Then upcoming in this mini-series, we're going to drill into the details and offer a few more examples. So let's just try it out here. Suppose a friend hands us a coin and says that they believe it is loaded. So of course, we ask why they think it's loaded. And our friend simply says that a stranger gave it to them and said it was loaded. So we're going to resolve to test this claim statistically. So for the sake of example, the coin looks like a typical coin. There's nothing special or remarkable about it. We have no external or additional information about this coin. So we're going to assume that this coin is not loaded, meaning that it is a so-called fair coin. So our research question is this coin loaded? Often formulating our hypotheses requires some subject knowledge. A loaded coin is a coin that is not fair. That is, either heads or tails do not occur with the same frequency. This is reflected here in our alternative hypothesis. Our null hypothesis, on the other hand, is that the true population parameter proportion of heads is 1/2. That is, that the coin is fair. So we're going to flip this coin 50 times and record the outcome of each flip. And by the way, our reference population can be described as a superpopulation, every possible flip and landing of this coin, or perhaps more accurately, every possible flip and landing of this coin over the next 50 flips over the next 10 or 15 or so minutes. So, okay, we're going to use a normal approximation here. And what this means is that we're going to take our sample statistic, namely the proportion of flips coming up heads, and convert it to our so-called test statistic, a standard normal or Gaussian quantile. And the name we typically give this quantile is Z. Now, our first step here in a traditional decision theory style hypothesis test is to specify our so-called critical region. And for the sake of expediency, what we're going to do is I'm simply going to fashion our critical region as all the values of our test statistic that are less than negative 2.3, along with all the values that are greater than positive 2.3. Now we're going to flip this coin 50 times, and let's say for the sake of example that these flips result in a total of 30 heads. So our sample statistic p hat is 30/50ths, which simplifies to 3/5. This result of 30 heads and 50 flips with a null proportion of 1/2 results in this value for our test statistic. And we're going to detail the calculation soon upcoming in this mini-series, so don't even trip on that. This test statistic does not fall in our critical region. It is neither less than negative 2.3 or greater than positive 2.3. Since our test statistic does not land in the critical region, we do not reject the null hypothesis. That is, we failed to reject the null. In our little make-believe experiment with this coin, our 50 flips or trials, we did not encounter sufficient statistical evidence to overturn our assumption that the coin is fair. And that's really all there is to it. Now, we certainly omitted some details, but they are just details. The important thing is that we executed a full-on, full-blown statistical test. And we're going to detail how we calculated both these steps, that is, create a rejection region, and how we transformed p hat into our z-score immediately upcoming in this mini-series. And later in this mini-series, we're going to work through a couple more examples. And that's it. That's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more Quantile.